you have full visibility into the product development activities. You have the power to drive change, to drive innovation, to see customer ideas getting materialized from product development, and talk with engineers within the company and bring all this together in order so that those are reflected within your product. So it's really an amazing thing. Yeah. And you have to ensure that the plane will operate smoothly, that it's going to be safe, that it's going to be stable, and so on. So this is a type of analysis with immediate impact. We're talking about human lives and thinking yourself in an airplane on air.
It's got to work. Yeah.
And if we want to think holistically as engineers, I know we like to kind of work in a specific domains, but we have to consider the whole stream, right? From beginning to end. Because if you say, okay, I'm a modeler, but then I don't know what's going on the solver side, you immediately break the workflow, immediately. Something that's coming up, it's going to change the way we do optimization. You see generative AI, the way we build models, the way we democratize knowledge among the different groups. And that is really going to help simulation go to the next level. When you bring more women in, you'll see a lot of diversity. You'll see a lot of unique solutions that haven't been there in the past. And this is really going to propel organizations to move forward in things that they have, in ways they have not thought about in the past.
Vicky Tsianika serves as the MSC Nastran product manager within the design and engineering group at Hexagon Manufacturing Intelligence. Additionally, she holds the role of adjunct professor at Oakland University, where she imparts knowledge in systems and industrial engineering, particularly focusing on AI and machine learning as they relate to simulation. With over a decade of experience spanning various positions in Greece and the USA, Vicky possesses a diverse background in simulation across multiple industries. Our conversation delved into her background, the current development and adoption of Nastran, and the integration of AI and machine learning into both product development and asset management life cycles in aerospace, automotive, and related sectors. Vicky's enthusiasm shines through, especially regarding early female STEM involvement and the progression of women engineers in the professional sphere. Do you want to start by giving a bit of background in terms of your career, your education, where you've come from, that kind of stuff, you know?
All right. Okay, let me first start by where I'm coming from. It's pretty obvious from my accent, but I'm going to say it again. I'm originally from Greece. I studied civil engineering back in Greece. I graduated from there, and then I came with a scholarship to the US just for PhD, master and PhD studies. In mechanical engineering, interestingly, it was not civil, but it was in the dynamics area. So dynamic analysis is pretty similar, just different structure. I completed my PhD studies here. I started working here in a pre and post-processing company. And then I pursued a second master's degree in data science back in 2020. And I joined Hexagon. Here I am today. I'm a product manager for MSC Nastran. And that's all about me.
Fantastic. Okay. Yeah, I noticed in terms of, well, lots of background really, but I'm just looking at your CV or your LinkedIn resume, as it were. So at the moment, you're working with Hexagon and also at Oakland University as well.
Yeah. Okay. This is a hobby of mine. I'm an adjunct professor at Oakland University. I call it a hobby because I love academia. I like teaching. I love keeping in touch with the latest developments in technology, and I feel that academia is the place for that.
Yeah.
So during evenings, I teach graduate or undergraduate classes, and mainly in the areas of statistics, machine learning, optimization, and so on.
Okay. So you're full-time with Hexagon, and you spend some of the rest of your time teaching in the university environment. Okay, that's cool.
That's correct.
Yeah, nice. Because I can imagine your job as a Nastran product manager keeps you pretty busy.
It's extremely busy.
Full stop, you know. Yeah. Okay.
But it brings a lot of joy as well. It's a fantastic work.
Okay.
Yeah.
Cool. Okay. Can we just focus a little bit on some of the background then? So you worked with, you mentioned the work with the pre and post company. So this is with Evotech CAE. So they're based in Greece. Is that right?
Yeah. Interestingly, yeah, I didn't join them while I was in Greece. I got to join them in USA. So they have a company in the USA here in Michigan. So this is when I got acquainted with them as an intern first. I started working with them with an internship, and then I continued full time with them. Yeah.
Yeah. Okay. Gotcha. So that was after your PhD then?
It was during my PhD, because there was
okay.
also some some, I would say, joint research with my research group and Beta. We used some of their tools, some of their technology. There was a lot of exchange of technology. So yeah, it was, I would say, my PhD was partially funded by Beta as well.
Yeah. Okay. So from my experience, Beta is very heavily involved in the automotive industry.
They are.
And hence where you are in the US, that sort of ties up, doesn't it? In terms of, I think that it's ANSA the pre-processor, isn't it? And then Meta the post-processors.
Exactly.
Yeah. Okay.
Yeah,
so
they have. Yeah.
Go on, sorry.
Go ahead. Yeah.
I was going to say, do they have a solver then that they
use? They do have a solver. Yeah, it's called the Pelices. They have like a plethora of different solutions from pre and post processing. They have their own solver, but they also have their own data management systems. It's a very broad portfolio encompassing a lot of different solutions. Yeah.
Okay.
For industries. Yeah.
Yeah. Absolutely. Yeah. I like to say, I know ANSA from the automotive industry in the UK. So yeah, not too familiar with everything else that they do. Okay. So can we talk a little bit about what you're doing with Hexagon then? And so your Nastran product manager role. I mean, that, there's a lot of stuff there, isn't there, that it's keeping you very busy. So how long have you been doing that?
It's been 2 years now. Unofficially, it's been 2.5 years that I have, because I had some transition time into the product management role. I started off as an application engineer with Hexagon in the ground vehicle team, focusing on automotive accounts. And then I moved on to the full-time product management position. It's keeping me busy, as you said, but it's a fantastic team, fantastic workplace, and a fantastic product, I would say. So I have expanded my areas of focus to all industries outside of automotive. So it's been a fantastic journey for me.
Yeah. Okay. And is the team fairly remote then, or do you have a Hexagon?
It is a remote.
Office?
We do have a local office, but the needs of the role demand that you talk with a lot of regions at the same time. So it doesn't really matter whether you're on site or not, just because the role is global. You have to talk with different geos during the day. Different geographic locations. Yeah.
Okay. So in terms of being the product manager, then do you sit between sort of strategy, software development, and what the field, i.e. the customers are interested in? Are those the three main areas that you're involved with then, would you say?
Yeah, very well put. Yeah, we're sitting right at the intersection of those areas that you mentioned. And that's what makes the product manager's role so unique and so interesting, because you don't lose touch with the customer. You talk with customers, but at the same time, you have full visibility into the product development activities. You have the power to drive change, to drive innovation, to see customer ideas getting materialized from product development, and talk with engineers within the company and bring all this together in order so that those are reflected within your product. So it's really an amazing thing. Yeah.
Okay. Yeah, I mean, I'm obviously very interested in the Apex to Nastran workflow. So there's a lot of development going on with Apex supporting some of the new Nastran capability as it's coming out. So how far ahead is the release from what you're working on now? What does that sort of development cycle look like?
Currently at Hexagon and for MSC Nastran, we're down to 2 release cadence per year in order to ensure that we have plenty of time to develop and to put more material, put simply into the product. So we are down to 2 release cadence. So it's pretty much, I would say, split equally within the year, 6 months and another 6 months. But of course,
okay. But there must be some aspects of the development that take longer than 6 months then. Is that right? So some things that are maybe planned for 2025, 2026, that kind of stuff.
It actually, it depends on the project. It depends on the kind of things that you want to do, right? The level of difficulty, how much time you want to invest on that project, because there's so many things you can do. Maybe you can draw a line, or you can say, I want to invest more. My customer is asking for that. There are a lot of different factors that you need to take into account while prioritizing and while, I would say, planning for the product. So I would say it's project-based, but there are a lot of factors going on in the background to ensure that the planning is correct. So for MSC Nastran, of course, we have big projects, small projects. It's a lot of different things coming together for each release.
Yeah, okay. I mean, from my experience in the aerospace industry, from a structural certification point of view, companies like to settle on a particular release.
Oh, yes.
For the the development of the aircraft, and I mean, you can understand why they want to have a stable version that everybody uses, but equally, it's sometimes frustrating because you might be working with a company. I mean, I remember an Airbus program where we were using a version that was, oh goodness me, maybe 7 or 8 years older than where we were, So in terms of the new capabilities, it was frustrating because we didn't have access to certain aspects of the what Nastran could do because we were constrained by that version. Is that
it's
something?
Still prevalent. Yeah, it's still prevalent, especially, its industry has those unique things that you're mentioning. That is more, I would say, applicable to aerospace. Automotive, we've seen a huge change over the past few years, and their adoption rate is much, much higher. So they'll move from one release to the other much faster than in the past. But this is the same even for aerospace customers, right? So they are now starting to adopt kind of faster than what it used to be in the past. But still, I would say, yes, you might see those kind of things where they are locked in a specific version for 8 or 9 years, behind what current MSC Nastran is.
Yeah.
Unfortunately.
I'm just thinking about some of the. So I've had a brief demo of Nexus Compute and seen the ability to access HPC, in the cloud on a subscription-based model, which is pretty cool, and doing that, you've got access to the latest versions, the latest parallelization, memory handling, storage, all that kind of stuff, So I mean, will Nexus Compute support legacy versions as well? Do we know, or is that something that's still up in the air?
We are actually working into, I would say, satisfying customers, and I would say we're customer driven at Hexagon, so it also depends on what the customer wants. And of course, because Nexus Compute is native, we aim to support our software to the utmost, right, and our legacy solvers to the utmost. But Nexus Compute brings into the table the elasticity of the cloud, right? That's an amazing thing, and seeing it applying to all the solvers within our portfolio is I would say, a fantastic step forward.
Yeah. Okay, that's going to open a lot of doors to people, isn't it? I think, with the versions of technology and the speed of solve and that kind of thing.
I mean, cloud computing, we all know the benefits. We've seen that, and there is a huge push now for organizations to migrate to the cloud. there's a lot of development in this area, and the things that you can do on the cloud without being limited by resources and by all this, I would say, constraints that we traditionally had. It's going to bring a revolution into the way we do simulation, right? And the way we utilize Nastran.
Yeah. That's interesting. Yeah. Okay. I mean, one thing, I was talking with a company last week, and I was pushing Nexus Compute, or a cloud-based system on them, or discussing it with them, and they were concerned about the security of their data. This was a defense company. So are there things in place to handle that kind of stuff? What's the protocol there?
Yeah, absolutely. So privacy is always a concern, especially when we migrate to the cloud. And this is not just for defense, but I would say for any other organization out there, they want to feel that their data is secure. And with this on-premises schema, they used to feel secure. They say, okay, it's on-premises, I have my data here. It's not going to be impacted by malicious attacks and whatnot. But now you have the option to migrate into the cloud and still reap the benefits of it without worrying about privacy, right? And those privacy concerns is something that, of course, we're working on, and we want to ensure that the customer is feeling 100% comfortable to deploy their operations on the cloud, while at the same time maintaining the level of security that they want. And the technology is there.
Okay.
It's not something new, I would say, something that
So it's more a mindset thing than a technological blocker for companies to be using this stuff.
Exactly.
Yeah. Gotcha.
It's a new workflow altogether, migrating to the cloud. And we're talking to customers, we're seeing this thing happening, but all those questions, we expect them to rise, right? We expect those questions. What is going to happen with my data? Where do I store my data? How do I pay for this? And all these questions that, traditionally they were not there because you had the on-premises schema. How is it going to benefit me?
Okay. I mean, and again, one of the things I saw was, well, whether this is hard at the moment or whether it's something that's going to happen, is the ability to fire up Nexus Compute directly from the Apex environment. So you can have a model architecture and fire, without having to deal with any file transfer or deck editing or anything like that. So that could be a pretty interesting way in which people work, couldn't it?
Absolutely, and I really am glad that you're mentioning that, because again, it creates a different workflow, right? You don't have to submit to your server. You don't have to worry about provisioning resources, parallel settings. Then something doesn't work, then you have to go back and so on. No, it eliminates this whole loop. So you stay within your pre-processing and post-processing environment. You fire up your run, you get your results, you have them back, and you're working undistracted, and without having to do all this, I would say, manual work. Let's say.
How did you get started with simulation? What were your first experiences with software, with learning? The whole process. How did that look for you?
Okay, I did mention it a little bit, but I'll be more specific. Actually, when I landed in the US, my very first 2 weeks, my professor, he was working back in the time in summary analysis work for dynamics, and he was looking at Greg Bampton and all these reanalysis techniques out there. So my very first task was like, hey, take this paper, please read it, see what Greg Bampton does. All this is theoretically, right? And then you can run those simulations on MSC Nastran. I started with MSC Nastran. It's the software I started with, and now I'm the product manager. So I've been educated on MSC Nastran. So
that was your first experience with simulation then?
Yeah.
Wow.
My very first experience with simulation was with MSC Nastran and HCMS. Believe it or not, So then, then I started modeling small things within MSC Nastran and seeing how they work, verifying manually whether dynamic run gives the same results, and start getting acquainted with that. So this is how I started.
And what pre and post were you using for that?
It was ANSA and Meta. Okay,
so you were building Oh, so you mentioned there was an answer sponsorship or involvement in the
Yes,
work that you
yes,
do. Yeah,
yes,
okay.
yes.
Gotcha. Okay. So you were building models and you were able to compare with physical data as well, were you?
Yeah, we did that as
Okay.
well within our lab. We had to, yeah.
What kind of structures were you looking at? Can you say, or was
Yeah. No, back in the time, we actually working with some major organizations, but honestly, we wanted to prove the technology. So they were conducting the physical experiments for us, and they were providing the data back to us that we had to verify with the simulation and with the new methodologies that we were building. This was not complicated testing. We're talking about the simple coupons, simple beams, and a lot of fatigue testing getting involved with some new technologies that we were developing back in the time.
Yeah.
And that's how it kind of worked.
Yeah. Okay. My knowledge of Craig Bampton is quite limited, but from memory, it sort of ties the structural FEA response to a kinematic dynamic response. I'm thinking about Nastran interfacing with atoms for the flex body stuff. Is that
Yeah,
similar?
simply put, it's a substructuring technique, right? The whole idea is to substructure efficiently and solve those matrices mathematically by substructuring them and then assembling it back together without having to use launches, right? Especially,
Okay.
launches now, it's becoming more and more impractical because of the size of the models, because of the frequency ranges. Especially in the automotive industry, you're going to see that the Lanczos is almost never used because we're talking about the 100 million degrees of freedom systems, right? With those battery models that come in. So you always have to use some subtraction technique, right? All the commercial solvers out there, they have their own proprietary version of CMS, component mode synthesis. It's called,
Gotcha. Okay, so day one you were straight into matrix methods to effectively result in more efficient Nastran simulations. Okay, that's a pretty good apprenticeship, isn't it?
It was hard, but it allowed me to learn a lot of things. And
okay. And then so from a formal learning perspective, I mean, did you take a Nastran course, or were you really learning from your peers in the department you were working in, that kind of thing?
Back in the time, I was learning more from my peers, yes, and from the users guides that were available. Also, MSC Nastran has like a lot of documentation, a lot of different things that it's provided with basic installations. I used to read those manuals in, so I actually trained myself. But simply,
okay. Yeah, I think a lot of people would say the same. I remember doing my doctorate studies with some abacus nonlinear work, and just banging my head on the table, trying to learn, understand things, trying to get things running, it's weird because some of the stuff, I mean, I developed an Apex for Sol 400 course 18 months or so ago, and there were things in there that I was refreshing my knowledge on, and new things to me, and thinking, oh goodness me, I wish I'd known that 15 20 years ago. The first part of the question is, what's the best thing you've seen with simulation? And then the second part of that is either what's the worst mistake you've made, or the worst simulation that you've seen other people involved with. Okay, so quite a big question there, really, but just wondered if you had any views on that.
Okay, I'll start with the best thing, not the worst one. And the best thing is also like something I learned quite recently. I would say it's not an analysis that I used to do throughout my entire career, and it's something that most probably know about. It's windmilling analysis. Especially because I come from an automotive background, not aerospace. So I find this type of analysis fascinating. And because it has, this immediate impact. You think of yourself on an airplane, just as a background. Do you want me to say what windmilling analysis is, or?
Go on then. There'll be people who don't know the basics.
put it simply, you're in an emergency situation. The engine might not be working, and this is an analysis happening during in-flight, right? It's an aerodynamic type of analysis where basically the airplane, due to the forward motion, there's still air passing through the blades, but there's no thrust at that point in time because the engine is not generating power, right? And you have to ensure that the plane will operate smoothly, that it's going to be safe, that it's going to be stable, and so on. So this is a type of analysis with immediate impact. We're talking about human lives and thinking yourself in an airplane on air.
It's got to work. Yeah.
And having to do this emergency landing. So this is the type of simulation that really has fascinated me, and due to its complexity as well. And I really kind of enjoy looking at this development.
And is this looking at the full air vehicle model, or just the jet response then?
Just the jet response,
just the engine response.
The engine,
yeah. Okay. So I knew it as a sort of rotordynamics type thing.
Correct.
Yeah. Okay.
And Nastran, this area is heavily being invested on. It's developed a lot. So as a product manager, we started this, and I started looking into that, and I was fascinated by the simulation itself, right? Let alone all the development details that go into that. Yeah.
Okay. So going back to your role as product manager then, and the interface between software development strategy and the companies that are using this stuff then. So you must see a big push from the engine OEMs to increase this capability to be able to solve more efficiently in a Nastran environment.
Correct. Yeah, that's correct, right? And it also, Steph, it has to do with this simulation. I would say it's a highly nonlinear simulation, right?
Yeah.
And when we hear nonlinear, we understand that the complexity increases exponentially.
Yeah.
So you have to keep investing in your methods. You have to ensure that your methods stay relevant, stay up to date, and that they're I would say propelled by computing as well, so that they run fast and so on. So it's there's a big push.
What solution sequences are used for that kind of work?
Solution 128 for MSC Nastran.
Okay. And is that part of rotordynamics then?
It is. It's the rotordynamics solution of MSC Nastran.
Yeah,
that's
correct. I can't say I've ever used it, but I know a little bit about the background of what's going on with that, So okay, no, that sounds great. Yeah. Okay, so the second part then. Pardon me.
That's the best thing, and you're talking about the worst now.
This is the thing I'm interested in. Yeah, the meaty subject. What's either the worst mistake you've made, or the worst use of simulation to try and solve a problem?
Okay, I'll tell you what. I want to reply to this question with a more general answer rather than being as specific as I was with the best simulation.
Yeah.
So
if you want to bring your lawyer in, that's fine as well.
No, it's not because of that. I'll tell you why I'm saying that.
Yeah.
The worst type of thing, like for simulation that I've seen, and it keeps happening actually. It's a very, I would say, common phenomenon. It's for people starting to solve something without knowing what they solve. So I would say that the worst thing is trying to solve a problem without first asking yourself the question, what am I trying to solve here? Like, what is the analysis I'm trying to do, right? And at least like for my experience, I have seen that happening more and more often. And this is why we have to adhere to strict deadlines. There are a lot of legacy decks out there, and we are all been there, done that. Your manager tells you, okay, take this deck, please run the simulation, make those changes, deliver the results by end of the week, and then you're like, oh my God, what is the simulation about? And then you're trying to make changes, and people make changes, engineers start making changes, but they don't know what the actual problem is. So instead of making things better, it becomes worse. And then you end up getting garbage results, garbage in, garbage out. And then you're like, what happened? So I say that's the worst thing I've seen with simulation. And honestly speaking, I guess we have to take a step back and remember again that we're talking about physics here. We're engineers. We really need to have a theoretical understanding of what we need to solve and not expect that the software just, boom, I'm pushing a button, I'm getting results.
Do you know what? It's sort of a byproduct of where things are developing. You know, software is much more easy to use, you know, so you can build great big models, you can solve them faster and faster. But like you said, the garbage in, basically you can go from garbage in to garbage out more quickly. You know?
Yes, exactly. And you know, even you're saying about building models, right? Even the building phase, without even considering about the solving, right? We use some modeling techniques. You're a fantastic modeler yourself, right? You've used it, you know about it. And some of the techniques are so bad for the next step, which is the solver, right? I'll give you one example that we've seen. Rigid elements, right? There's a lot of abuse with rigid elements, especially in automotive industry. You create those humongous spiders. We're talking about 2,000 legs, 3,000 legs, right? And then you try to solve it, and then the solver complains. And I'm not just talking, every commercial solver say, hey, look, this is really big, I cannot process it. But the engineer did not spend the time beforehand to say, hey, this is not a good modeling practice for downstream. I really need to ensure that I'm applying the best modeling practices, right? From a physical standpoint, because the software can really do anything. You can open Apex, you say, okay, I want to distribute this this RB, and it will do it for you. But does it? Is it a good practice? That's
I mean, one of the things, I mean, I wouldn't say it's cliched, but it's certainly spoken about a lot. So I do assessment for NAFEM's professional simulation engineer thing. So we interview people at different levels to you know, gauge their understanding and ultimately whether they're going to be safe in terms of using simulation in their jobs. And you know, it's always, for me, it's always a case of, can you break something down into its fundamentals, both in terms of the physics, both in terms of the simplicity and the elegance of the model, you know, and once you know where things are working at that level, that's when you start to add more complex, you know, more complexity, more detail, you know, more load cases, blah blah blah, before you just press the button and expect, you know, a terabyte of result data that's going to make everybody happy. You know, it's it's an issue, isn't it? It is an issue. Okay. I mean, I think you know, the ability to solid mesh stuff very easily is great in some ways, but not that great in other ways, you know.
Exactly.
You know, because you generate these monster models before you go anywhere near the solver. So okay, that's definitely something that that needs to be thought about, isn't it? Okay.
Exactly. And if we want to think holistically as engineers, I know we like to kind of work in a specific domains, but we have to consider the whole stream, right? From beginning to end. Because if you say, okay, I'm a modeler, but then I don't know what's going on the solver side, you immediately break the workflow, immediately. Because you're going to deliver something to your counterpart that it's not working, and then this is where the mess starts to happen.
Okay. How many excuse me, in terms of the companies that you work with, do you see people having rigid workflows set out for them, or do they have freedom to make mistakes? You know, that I mean, you know, that's something that can be controlled quite carefully, isn't it? Do you see differences in that kind of control?
I think it is changing rapidly. There used to be more space for mistakes, more space for experimentation.
Yeah.
But now with the push for automation, I think that this is going away. We're trying to automate more and more, and that during this process, we're stripping away the engineers of their ability to think in a more holistic manner and to understand the workflow from beginning to end.
Yeah. Okay. I mean, that's an issue again, isn't it? By constraining people to make fewer mistakes, you're removing some flexibility for them to do other stuff, aren't you? You know, or to look at problems in slightly different ways.
Not only that, Steph, I think that by trying to automate to actually reduce the mistakes, you're actually producing more mistakes because engineers don't know what's happening throughout the whole process. So if a mistake occurs, then there's going to be a lot of delay. You have to speak to that person who did the automation or data expert, and you don't really have the bandwidth yourself to say, okay, this is where it started, this is where it ended. What happened? What happened during this workflow, right? You didn't have the visibility. You're working here, and once something breaks down here, then what do? You have to talk to someone else, delays happen, and so on. So the mistakes take more time to resolve.
Yeah.
There should be a balance in between. I'm not saying I'm against automation. Absolutely. Automation is really needed. It makes people feel more comfortable. It really democratizes knowledge. But at the same time, engineers should definitely know what's going on in the background, not just pushing buttons here and expecting things to magically work.
How much theory do people need to know? You know, I mean, that's a difficult question, isn't it? You know, I remember speaking with one of the other guys on a similar conversation. You know, do you need to know all of the solver details? Do you need to know all the shape functions? Do you need to know all that stuff? I mean, for me, I think it's as long as you have an understanding of what's going on and be able to spot where the errors are, that's good enough. I mean, what do you think about that?
Okay, it depends on the way you phrased it. Now it depends on what do you mean by theory, right?
Okay.
Generally, you're talking to an academic as well. I'm a huge proponent of theory. I will tell you a lot. The answer would be a lot. I believe that, as we have discussed so far, you really need to have a fundamental understanding of the physics. Otherwise, you don't really understand what you're solving, and the results that you're going to produce are going to be meaningless, right? At the same time, how much in depth you want to go, well, it depends on your role. It depends on your career aspirations. It depends on the level of, I would say, whether you want to be very, very skilled in a specific domain or where you want to have a broader understanding of things. But in any which case, I feel that theory is extremely important, especially in our profession, in order to understand what's going on. And also for emerging technologies, right? This is something we might discuss about AI, ML, right? You really need to have an understanding of the theory to know how the models work so that you don't actually utilize black boxes. And I think that with the automation, that's where we're headed as well as engineers, right? We're utilizing black boxes sometimes without knowing the fundamental physics. I'm not saying you should know the shape functions, right? For finite element analysis, but you should know why they're important, right? You should know basic element formulation so that you don't abuse the elements you're using in your analysis, right? And this type of things.
Okay. I mean, how much can the sort of software experience, you know, obviously I'm thinking about Apex building and that kind of stuff. How much can that help somebody, you know, opening up the black box to see inside to say, okay, do you really want to use this element type? You should be using maybe this element type. You know, what do you think about that?
I think, okay, that comes from experience, definitely. You really need some experience into that, some empirical knowledge of what are best practices, what are not good practices for your simulation analysis. But at the same time, you have the option to open a user's guide and really glimpse through the actual settings. So, for example, a quad element, okay, what is a quad element? What is a tria element? What are the differences? And really have some basic understanding. I'm not saying you should know everything about it, right?
Yeah.
Know how dynamics work, know what an equation of motion is, how matrices are decomposed, why one solver versus the other, right? Not expect, I shouldn't expect Steph to tell me, okay, MUMS is the best solver. Why? The next question is, why is MUMS the best solver? Why should I use the CAE solver for solid dominant models? Am I expecting Vicky to tell me this is good without me knowing about it?
Yeah, okay. Yeah.
So you really have some fundamental understanding is really important, I would say.
Yeah, okay. Actually, okay, if we're talking big topics, we're going to go into a really big topic now, something that you're very interested in. So I've got a question here. How did aircraft fly before simulation? Or how did cars drive, ships sail, etc.? How that's looking backwards, looking into the future. How is AI and data science and machine learning, big keywords you'll find everywhere, all over LinkedIn and Google and blah blah blah. What? Just give us a little bit of your take on that as a subject, and then see where you think things are moving or headed.
All right, so for simulation, especially for simulation, I like to think of three big areas: before simulation, simulation time, and the future, right?
Yeah.
Before simulation, okay, we're talking about a lot of theoretical analysis, empirical knowledge, physical experiments that would actually lead you to the results, right? And this is how, as you rightly asked, aircrafts flight, or we drove the vehicles on the road, right? It required tremendous amount of manual work, and of course they were not as technologically advanced as they are today, right? Now with the advent of simulation, I don't know, things came upside down, right? We're talking about a lot of physics at the same time. You can really have large models. You can do multiple types of analysis, all that very, very fast, right? And combine, fire up a lot of digital simulations, and then have your results on your computer work as an engineer. That's been fantastic, and it still is, as a matter of fact. We're not yet where we would like to be when it comes to artificial intelligence and machine learning. This is something new that's coming up, but of course it's going to revolutionize the way we actually work as engineers. Again, I'm not saying that we're going to fly in the future or drive in the future without performing simulations. I think this is going to be paramount, the way we work, but the work is going to be less, right? We've already seen, I recently went to San Francisco, actually, and I was really intrigued by those driverless cars. I don't know whether you've seen them.
I've not seen them in real life, no.
It's absolutely, I mean, you're like on the road, and then suddenly there's a car passing in front of you, and the steering wheel is moving, but then there's no driver. And you're like, oh my God, this is fascinating. And then I said, I really want to get into this car, but the demand was so high that it was impossible to find a spot. But anyhow, I'm not saying that we'll get there and we'll have everything sorted out when it comes to artificial intelligence and machine learning in the next 10 years, but it's definitely something that's coming up. It's going to change the way we do optimization. You see, generative AI, the way we build models, the way we democratize knowledge among the different groups, and that is really going to help simulation go to the next level.
Yeah.
Faster, more efficient, and so on.
I suppose, well, that there's obviously a benefit there with those technologies, but there's potentially, we talked earlier about having, a theoretical understanding what's going on. In some ways, that those processes are going to remove the need for those fundamental building blocks of understanding for an engineer, aren't they? Or they could do.
It depends, right, Steph? Because that's a huge problem currently. And to put it formally, in I would say machine learning terms, it's called transparency. And that's a huge problem for organizations. Why? Because when you create a machine learning model, right? Let's say I'm Vicky, I'm creating a machine learning model. I'm putting in the data I want. I create the model and I give it to Steph. And Steph is I enable interdisciplinary collaboration, which is fantastic. But Steph has absolutely no idea how this model was created. So does it give me correct results? I don't know. Is it something that has a bias baked in? That can be the case even for engineers, and that might be the case, and it might have real life consequences. So transparency is extremely important. So again, going back, I believe having a fundamental understanding of engineering, we're talking about physics here, and then how we can apply those into machine learning model is going to be the driving force to moving efficiently to machine learning and AI workflows in the future for engineering.
Okay. So maybe the black box needs to be a transparent box, a see-through box. The see-through box.
Exactly.
The black box becomes a see-through box. There we go. Yeah,
that's a good point, actually. That's what I'm going to say. It has to be a see-through box, at least in an organization internally, so that you know what you're using.
There you go. There's the punchline of the video.
That's the punchline.
That's what we're going to see on LinkedIn. Yeah. Okay. Yeah, that's interesting. So in terms of your work as a professor, then, or your academic work, is that looking at data science in more general terms, or is it focused on engineering and simulation?
No, it's data science in a more generic way. I do teach in the industrial and mechanical engineering department, but again, I would like the students to have a fundamental understanding of how models are getting created, right? How those models are created, and then feeding in those data, the engineering data. That should be the easy step. I'm putting it in quotes. It's not as easy, but especially for physics based. But have a fundamental understanding of how to develop these models, how to pick the right one for your simulation, how many features do you need to use, and all this kind of things. But it's more generic, I would say. It's not just simulation.
Yeah. Okay. And are there software tools, mature software tools, to allow you to do these kinds of things then, or are people still having to write stuff themselves?
Excellent question. There is another term over here that people use, which is called the low code to no code approach, right?
Okay.
And especially for engineers, this becomes super important. At Hexagon, for example, we have a tool called Odyssey. It's our machine learning solution, and it works fantastically for engineering problems because it gives you that see-through option, while at the same time you as an engineer do not have to develop all these models yourself. So let's say, for example, you want to create an MSC Nastran surrogate model using some proper orthogonal decomposition technique and create a reduced order model with design of experiments or with experimental data, and run a nonlinear analysis problem and create that surrogate. You can definitely do that without having to do code, without having to do all this, and go from beginning to actually animating your results, which are now coming from the machine learning model, not from simulation.
Okay. So there's like a building block approach using the tools to put the chain together, as it were.
Exactly.
Okay.
It's the same thing, Steph, as you will see, for example, when we started the pre-processing, right? And it was the building block for the solver, right? It's the same thing for those products like Odyssey, for example. They provide the user the convenience and the user friendliness that it's needed in order to build those machine learning models without having to know in the background all the intricate details of proper orthogonal decomposition, right? They do that on the background.
Okay. And has Odyssey come from an engineering simulation background then? It has.
Yes.
Okay.
Yes.
Yeah. Okay.
And then the developer, he's I would say has a fantastic engineering background, while at the same time applying those machine learning methodologies into the product. So it's a very good amalgamation of both worlds inside one product.
Okay. No, it's good. I mean, it's something that I need to look into in more detail. You know, the bulk of my customer base is running, fairly simplistic, static type problems. They're not really looking at these sort of development type avenues, but I'm sure it's going to become much more apparent across lots of different industries, isn't it?
It is, and it's a matter of, Steph, also putting the historical data in, for example. I understand we're talking a lot about synthetic data and designs of experiments where you can explore the whole design field, but there's also the, I would say, the aspect of historical data. Organizations have tons of them when it comes to material, actual data during driving conditions and whatnot. And this is a real treasure. But they don't have now, I would say, the tools to actually exploit this treasure to their benefit. And this is how machine learning comes in. He says, give me those data, and I'm going to run the simulation for you while training that simulation on those data, right? And this is where the power of machine learning actually shines and brings this unique value.
Yeah. Fantastic. And you must see lots of companies who are really at the forefront of this kind of development and research and development,
Yeah, and one more thing, for example, that comes to my mind about, because we spoke about artificial intelligence and machine learning about, and you spoke about simulation in specific. I'll give you one more example that actually is very prevalent. You're bridging simulation with manufacturing, and you're putting those two worlds together, right? We use the term digital twin, right, more and more often. But I'll give you one example that I really like. Let's say, simply put, that you have built your digital twin for simulation, right? And usually we can call an FEA model a digital twin, right? But now you're taking it a step further and you're putting a machine learning model, which is much more efficient and it runs faster, and so on and so forth. Now, what you can do is you can actually take data from the field using IoT sensors. Let's say you have a vehicle, it's running, and so on, and you can put those two together. So you are making a digital twin, but now it's for operation. It's not for design, as it has traditionally been. So what do? You have simulation here on one hand, and you know what the behavior is. You have the digital twin for operation. It's getting data from your IoT sensors, and then you actually compare those two in real time. And then you see that the operation tells you, no, there's something going on here. You have put those thresholds, but I see those results not correlating, which means that the health of my asset it's not good. And this is how you open the door to actual designs for operation, digital twins for operation at this point in time.
Gotcha.
So you're bringing the world together.
You're looking at the condition of the asset in real time and comparing back to the simulation.
Exactly.
Does it make sense?
Exactly. And all this is done through the digital twins for operation, which really opens the doors to predictive modeling, predictive maintenance, and so on. Because the moment something goes awry, the health of the asset is not good, you're notified, and you know that.
You probably have thought of this already, but going back to the windmilling analysis that you were talking about early on, that digital twin approach can predict it's going to happen before it happens, potentially.
I did not think about that, but that's a fantastic example of how you can build a digital twin for operation, because you have the sensor and you know beforehand that something might go wrong, right? And you're comparing. That's what we mean by saying we are comparing in real time. But this time you're not running simulation. You have trained your model using a machine learning approach.
It's massive, isn't it? That's a massive topic. Massive. Well, one of the points question that you suggested, Vicky, and thank you for that, that we'd like to touch on is, through my career as an engineer, perhaps if I frame it from my perspective, first of all, I would say that my university studies, my introduction into the working environment, my career, the people I work with now, it is massively a male-dominated environment. Okay.
That's what.
there you go. The floor is yours. What do you think, and what would you like to say on that topic then?
All right. I'm glad we're discussing that because this is a topic very close to my heart. And I always like to discuss this openly so that we encourage more and more females to enter the simulation world. Before I talk about CAE and simulation in general, I just want to talk about STEM, right?
Okay.
We women engineers and in STEM roles can really be role models for young females, right? And we can really inspire them to follow a similar career and form and shape those aspirations for them and break down barriers, right? You have seen a lot of studies about women feeling underconfident compared to their male counterparts, and that's not. It starts from elementary school. There's plenty of research. It moves to middle school and high school, and then even during your professional life, you still feel underconfident, right? I cannot make it. I'm not as good in this domain as a male is, and so on. And there are also those stereotypes. Since this is like a nice discussion, I want to bring you a real example. People say, oh, no, this is not the case anymore. While I was working back in the time as a support engineer, right? And we used to frontline support, you used to pick up the hotline and say, hey, how can I help you today, right? And it's usually, I used to pick up the calls, and sometimes, people would tell me, can I please talk to an engineer? Making automatically the assumption that I am not in the engineering world, right? This is the kind of stereotype we don't want to perpetuate. Now, moving on to the CAE world and specifically simulation, again, we need more women. They bring a diverse perspective. We can work together to bring unique solutions together. And as a last point over here, and again, this is something I always say, having more women in those type of professions, and let's talk about CAE or simulation, it's not about fairness. You're not making a favor to anyone by saying it's a matter of fairness, bringing more women in. It's a strategic imperative, right? When you bring more women in, you'll see a lot of diversity. You'll see a lot of unique solutions that haven't been there in the past. And this is really going to propel organizations to move forward in things that they have in ways they have not thought about in the past. So
I can see that. I mean, two things from my point of view then, or my thinking. So when I took my degree in mechanical engineering, in goodness me, when did I start? Well, mid 90s. Okay, I'm very old.
No, you're not.
So the mid 90s, there were 100 students in our intake, and there were 4 girls from that 100. Okay, so you'll see this a lot more closely than I do. In terms of perhaps some of the engineering courses that you see through your teaching and the institutions that you're affiliated with, do you see that there are now more girls coming through?
Yes.
Is that happening? Yeah.
Yes, it's happening. It's an upward trend. That's a very good thing. We're still not where we want to be, but I would say that you see more and more women going into pursuing this type of career. And it also actually depends on the type of engineering, right? Because for civil engineering, it was during my bachelor's degree, it was a good split between males and females. But when you go to mechanical, this is where things change completely. And you see, as you say, 4 or 5 women compared to like 95 men in one class. It has changed, absolutely, but still it's not a 50-50%. Really. We still have a long way to go.
Okay, but the trend is happening.
The trend is happening.
So students, female students, as they're studying and looking at university options and what have you, they won't see that massive disparity anymore. Whether it's 70-30 or 60-40, whatever, it's much, they know that they feel much more comfortable in that environment because it's a more diverse environment.
Yeah, and because we, and I'm talking we all of us together, we realized that this is a problem, right? And it makes me extremely happy to see, for example, men like you coming out and say, hey, I see this disparity, but then at the same time, I really encourage more females to join. I really want them to pursue such a career because I find them equally successful, equally intelligent, and I feel that they can contribute a lot. So yeah, it's happening. We recognize that this is a problem, and I guess it's going to be resolved within the next years.
Yeah. I think, I don't know whether it's sort of related, I suppose. In some ways, certainly within the UK, when I was looking at my options for university study, it sort of felt like engineering in general wasn't as worthy a choice as some of the other things like medicine or law or accountancy. Do you think that's changing?
I think it is. It depends also, because for me that was not the experience. I had the grades to go into medicine, but for example, in Greece, engineering is a very, very prestigious choice along with medicine.
Is it? Wow.
And I feel that that's the same in the US kind of, but again, I haven't experienced that firsthand, I would say.
Yeah.
But I have experienced, less prestigious choices within engineering and more prestigious choices, right?
Yeah.
So yeah.
My partner is a doctor. She's a GP in the UK,
Nice.
obviously, and her maths, her brain is way better than my brain. And I'm going to ask her, why did you choose medicine, not engineering? I've never asked her that question. I'm going to ask that question. Yeah. Cool. Thank you, Vicky. We've covered lots of things.
Steph.
We've covered a lot of things there, haven't we?
Yep, and it was a very good and productive discussion. I'm glad we had this today.
We've covered lots of things there. Yeah.